Hi, I'm Mira Kuntawala, and this is my Lab 3 for Physics 1. The objective of this lab is to find the mass of a black hole in a universe where a star orbits a black hole. What makes this lab unique from the labs that we've done in the past is that we're using the motion points that we have to help us find a value that we're missing. Whereas in the past, we've used all the values that we've known to help us predict the motion of an object. For this lab, some of the information that we're given that will be useful to us in our coding is that the system is the star and it's orbiting around its source, a black hole, that's given at a certain location based on what we have on WebAssign. The only known force is the gravitational pull. The star's mass is given and the star position data is given in a CSV file. Delta T is also equal to the number of seconds in one day. The results of coding showed that the black hole had a mass of about 3.18 e to the 31. The fundamental principles that were used in this experiment were, of course, momentum principle, which states that the change in momentum is equal to the net force times the change in time, which can be rearranged to say that the net force is equal to the change in momentum divided by change in time, or F net equals dp over dt, which will be very useful to us. Secondly, Newton's universal law of gravitation, which states that the gravitational constant times mass 1 times mass 2 divided by the magnitude of the position vector will help to give us the value for the force of gravitation acting on the star by the black hole. If we were to try to solve for the mass of the black hole analytically, here are some of the steps that we would use. We would first try to find the magnitude because we have the position data of the star. Then we can find velocity by using the position data to find the change in the magnitude, which we just found, divided by the change in time, which is delta t. Then, multiplying that by the mass of the star, we can find momentum. Then, since we have momentum, we can find the change in momentum and then use the delta t that we were given earlier to help us find the force, which we then can plug in and isolate the mass of the black hole, which is what we're looking for. Now, what we're going to do in the coding will help to find this answer without having to do it analytically. So the first change that we make is helping to specify the black hole as an object that we want to represent, and by sphere, and then the color and the radius. Next, we add in the star's mass, which was given to us, and the black hole position, which was also given to us through WebAssign. Next is delta t, which we specified earlier. Then, moving on, we identify the CSV file based on how it downloaded from our computer, and then we show how to compute the x and y components of velocity. The x component of velocity didn't change, but computing the y, I helped match what the definition of computing x was. Next, we have the while loop, and here we've changed a lot of different definitions of formulas. The first being how to calculate initial and final momentums. Initial momentum is just the mass of the star times the initial velocity, and then the same thing goes for the final momentum. Then the change in velocity is just like we would think, final minus initial, and the same goes for the momentum. We also then specify that dp over dt is equal to delta p divided by delta t. And we also specify again that f net is equal to dp over dt. Then we go on to help define what dp dt parallel and dp dt perpendicular are equal to. We specify p hat and the magnitude, and then multiply those together to give us dp dt parallel. And then again reiterate that f net parallel is equal to dp dt parallel. Then for perpendicular, dp dt perpendicular can be found by subtracting dp dt total minus the parallel, because the parallel plus perpendicular gives us the total force. Next, we specify big G, the gravitational constant, and then we define the force here. So black hole dot mass, which is what we're trying to isolate in the equation, is equal to the magnitude of the net force times the magnitude of one of the star's position minus the black hole's position squared, divided by gravity times the star mass. We then define an arrow scale, and then also for the print statement, we add in black hole dot m so that we can see what the mass of the black hole is. Here's what happened when I ran my code. Now, it doesn't show the full orbit, and that could be due to several different reasons, but what we can observe is that if it had fully orbited, we would have been able to see the different 3 different arrows along their correct axes. And here in the output window of the Python shell, we can see that our black hole mass is the last number in the parentheses. Now to address the what does it mean and what if questions. For the what does it mean question, FNet, FNet parallel, FNet perpendicular, and dp/dt, dp/dt perpendicular, and dp/dt parallel are equal to each other values. However, they are found in different ways. For dp/dt and its two components, these are found by observing the object's motion, because dp/dt can be equal to the change in momentum over the change in time. Then for the net force, that's going to be the sum of all the interactions. In the case of this lab, gravity. And for the what if question, if we were given a mass, a black hole with a different mass, but the same initial conditions, we wouldn't be able to calculate a different mass simply because we would have the same starting information, the same force, and the same motion. Thank you.